So one last example of being able to work with our vector value functions and projectile motions. Let's say we have a baseball and it's hit at 2.5 feet above ground level at 102.3 feet per second with an initial angle of 37 degrees with respect to the ground. We're going to create a vector value function. We're going to determine the maximum height of the projectile, and then we're going to determine if it's hit in such a direction that there's a 10-foot wall that's 360 feet away. Will the batter hit a home run? In other words, will the ball clear that 10-foot wall? Right? So the first two of these we've done already in the previous example, or at least this type of problem. So let's get to it. Our function, which we can call r of t, is going to be equal to the initial velocity, which is 102.3, times our cosine of the angle, which is 37 degrees, times t, and that's in the I direction. And then in the j direction, we have the initial height, which is 2.5. We have the plus, I'm just going to skip down to the next line, 102.3 sine of 37 degrees t, and since it's in feet per second, minus 1/2 times 32 t square j. All right. Now, what I'm going to do is I'm going to approximate these trig functions to the nearest 10th place. So r of t, so we have 102.3 times the cosine of 37 degrees, and I get 81.7 t in the I direction, plus 2.5, quantity 2.5, and if we do the same thing but replace that with sine, that's going to be 61.6 t, and then minus 16 t squared, and that's in the j direction. And just like we did before, we could define a function x of t to model the distance traveled horizontally. So that's 81.7 t. And a function y of t that's going to model the path in the y direction. So that's going to be 2.5 plus 61.6 t minus 16 t squared. To find the maximum height, and this is part A. Part B is the maximum height. We're going to find the derivative of y to find the optimal time. So that's going to be equal to 61.6 minus 32t. And to find that, we set that equal to 0 to find the optimal height. That's going to imply that t is 61.6 over 32, and I'll approximate that, and that's going to be 1.925 exactly. Now that's not the distance, okay, or it's not the height, excuse me, that's just the time. So it takes about 2 seconds, so that's in seconds. So it takes almost 2 seconds for it to hit the maximum height. And so y at 1.925 is going to be equal to 2.5 plus 61.6 times 1.925 minus 16 times 1.925 squared. All right? And I'm going to plug that into my calculator, and that's going to tell us how many feet the maximum height is. So 2.5 plus 61.6 times 1.925 minus 16 times 1.925 squared. Right? And the maximum height is going to be 61.79 feet. All right. And so the last question is one that we haven't looked at yet. So to hit the ball, or to hit a home run, there's a fence that's 10 feet high that's 360 feet away. Given the above scenario, will the batter hit a home run? So here's how we can do that. Let's figure out when the X is 360 feet, and then we can plug that time into the into the t and see if 10 is bigger, or y of t, excuse me, is bigger than 10. All right, so and we know it's going to be a projectile motion, so it's going to do one of these sorts of things. All right. And so the hope is, if this is the wall, that's the intended path. That's what the batter wants to happen. All right, but it could happen that the batter hits it and then it hits the wall at some point. But regardless, this distance right here is how far it is of x of t. And that's actually going to be 360 feet. And what we're looking for is we're looking for the y value. So y at t is equal to what? And it's either going to be something like this or something like this, where it's going to either hit the wall and the batter's only going to get a double or a single if they're really slow. And then y of t is going to be, or if it's over the wall, then it doesn't matter how slow they are. All right, so now remember x of t, we found that earlier, and x of t was 81.7 t. And that's going to be equal to 360. That's easy. So we just divide 360 by 81.7, and we end up with 4.4 approximately, and that's seconds. So now we're trying to find the height after 4.4 seconds, and we're hoping it, or the batter's hoping it's greater than 10. So y at 4.4 is going to be equal to 2.5 plus, I think we had 81 or 61.6 times 4.4 minus 16 times 4.4 squared. All right, so I'm going to throw that into the calculator. So 2.5 plus 61.6 times 4.4 minus 16 times 4.4 squared. All right. And we get a value of negative 36.22. All right. And so what that means is the path that it took actually looks like this. So it's clearly hit the ground before anything. All right. And that kind of makes sense, because if we go back, remember the optimal height was at about 1.9 seconds, so about 2 seconds. So after about 4 seconds, we should approximate it, actually a little bit less than 4. It should hit the ground, since that the parabola is almost symmetric about the origin, okay, or at least from the origin, excuse me. All right, so we're going to say, since negative 36.22 is less than 10, okay, the batter did not hit a home run. Okay. In fact, the batter probably popped out, since the optimal height of the ball was 60-something feet. All right. The problem was that the batter didn't get enough launch angle nor velocity on the ball. All right. So if the initial velocity was a little bit greater, then the batter probably would have had a home run. They were probably really close to one, but unfortunately just allowed out. All right, so hopefully this shows you an application of where we can use projectile motion in real life. The next video series is going to start talking about normal vectors and tangent vectors.